Good morning. It's still morning. I nearly went afternoon then. Good morning, Year 11. It's great to see you guys. We're starting a brand new topic today. We're starting GCSE kinetics. So I'm just gonna. I'll share my screen. Share screen. Boom, boom, boom. Go. Right. Taking a while. Laptop's really struggling a bit today. I'm gonna try and sort that out over the weekend. I want that one. Oh no. Oh no. It's gonna come through loud. Sorry. Hang on. I'm on it. And my laptop's really struggling at the minute, guys. Pause. Good morning, Year 11. Pause. I think I've paused it. I'd love to just make that disappear. It'd be so much better if it was just to disappear. And because all I actually want is the chat. Okay, cool. Well, we're back. Okay, guys. Fab. So straight over to here. That's the end of my AS lesson on atomic structure. Loving it. So you guys, 11A kinetics lesson 1. Right, guys, today's lesson, we are starting GCSE kinetics, and this is lesson number 1 of the topic. Do you know what, guys? What I'm going to do is I'm just going to say, because my laptop is struggling a little bit today, I'm going to end the Google Meet conversation as well. I'm going to end that, but what I'm going to do is at the end of the lesson, I'll log it back in again, just to say goodbye to you guys, if that's okay. But I'm going to end it because it'll speed up my computer a bit. So I'm going to end it now. Sorry, guys. I'll see you at the end. Cool. Okay. So kinetics, lesson number 1, and 3 learning objectives today, folks. See if I can just move that up a bit. Can I? No, it's not. It's the laptop's going. No, not doing it. So we need to do 2 things. Number 1, we need to know the rate equation. To be fair, I kind of feel like I need to explain the term kinetics in terms of rates anyway. So we probably ought to put those. I'm going to add those to my learning objectives. So I need you guys to understand. Yeah, let's change my pen color and size. So I need you guys to understand what rate in chemistry means. Now, the great thing, of course, is that actually is the same thing as the rate equation. The word rate actually is explained by the rate equation. So that's quite nice, this. I also just want to talk about the word kinetics. Yeah, this word isn't used enough. Lots of teachers will just teach this topic as kinetics lesson 1, and they'll just call this rates lesson 1, otherwise known as rates lesson 1. And it's a really bad idea as a chemistry teacher to ignore the word kinetics. The word kinetic, I think most people would recognize this word. Wow, very laggy. No, I know, Atio, I know it's very laggy. I apologize for that. As I said, you will just have to stick with it. Yeah, the lag is a good couple of minutes, but we'll deal with it. So, okay, so kinetics, what is rate? So this is about rates of reaction. So let's put in some notes into our books. Okay, now that you guys have got your learning objectives in. Okay. A chemical reaction can have its rate. Notice my capitalization. Now, this word can have its rate measured. Now, at this point, I'm going to say a word from physics that you are never, ever allowed to say in chemistry. The word speed. Yeah, speed can never be used in a chemistry setting. The reason being is speed is changing distance over changing time. Yeah, distance over time. That is a different equation from rate. Yeah, so if you ever find yourself writing down that disgusting, Mr. Duncan, can you check your Hangouts, please? Kayla sent you something. Okay, can. Hang on. You're distracting me from my lesson. Okay. No problem at all, Kayla. You can then rewatch. Yeah, so if your YouTube is blocked, you can always watch the lesson back. The great thing about YouTube is at least it's recorded. Yeah, that's totally reasonable. Understood. No problem. Okay. So going back to this, a chemical reaction can have its rate measured. So what is the rate of a chemical reaction? So we now pick up an equation. So rate equals change. Now, you guys remember this already from energetics. This is a capital delta. This is delta. I'll actually have to put capital as well. This is a capital delta. Now, in chemistry, capital delta and mass, it means change in. Yeah? So this is the change in concentration of product. I'll actually write those words down. Change in concentration of product over change in time. Now, just to also mention, you can actually do the change in concentration of reactants as well. We tend to prefer to measure products, but it's not always possible. So we can actually measure it in two ways: concentration of product or reactant. Yeah, and you can add that product just there, just that little word, product or reactant. Cool. So now what we can then do is we can just look at this as we can do what's called a thought experiment. Yeah. So I just want to put this into context. So let's say we do a chemical reaction. Let's say we take a boiling tube. We're going to add a small amount of acid. Going to add some HCl. I'm then going to add some limestone. Hello, Mr. Limestone. Calcium carbonate. Limestone. There we go. And acids, of course, are all aqueous. Now, can somebody on the chat, please? Oh no, I need to go to school and go and get a whole load of stuff. I've left a whole load of stuff in school. That's driving me absolutely bonkers. I need to go and get it. I'm going to go and get it after. I'm going to go get it after this lesson. Right. So on the chat, please. What products am I going to make in this reaction, please? Let's do the equation. Calcium carbonate plus HCl. What am I going to make, please? Off you go. So the next thing is I'm then going to add to this, and you guys can do that question. Oh, I'm actually going to go like that. Cork, bung. There we go. Man, my diagrams are amazing. There we go. Thank you, Hao Ping. Great job. Well done. Yeah. So we're going to get calcium chloride. The calcium will steal the chlorine and become calcium chloride. And well done to Hao Ping for giving me the correct formula. What Hao Ping said, because I'm too slow at typing. Amazing. Yeah, we're going to get H2O and we're going to get CO2. Now, CO2. So what we can do is we can now measure the easiest thing to measure in this reaction. The easiest thing to measure would be to measure the carbon dioxide output. Gases are really easy to measure. So to measure them, can you just make a little note to Bene? To collect gas, we've got two options to collect gas. Method number one is we're going to do water displacement. Bad method, because carbon dioxide is soluble. Displacement, that's when you bubble it under the water and into a measuring cylinder. The other one is to use a gas syringe, far better. Gas syringe. Okay, so we're going to collect the gas syringe here. Now, what we're going to do is when the marble chips go in, all we're going to do is as the time progresses, so our result table is we've got time in minutes perhaps, and then volume of CO2, vol of CO2. So we've got minute 1, 2, 3, 4, 5, 6, 7, 8. So at the beginning, as soon as that acid drops in and I put that cork on it, we're going to see it being given off. So we're going to form, so let's zoom in. Let's do 10 centimeters cubed at the beginning. Then we're going to have 18 and then 15. Oh, hang on a sec. Sorry. That's not going to help, is it? 10, and then we get to 18, and then we get 23, and then we get 25, then we get 26, and then 26, and 26, and 26. Okay. So what we can do is we can see I like how we are all very lazy. Yes, Atiya, I agree. So what we can do is we can see that the volume of gas is increasing, and it took 8 minutes. So by the way, the reaction finished. So the reaction finished here. Yeah, there was no more gas being made. So we can work out the rate of this reaction. We can say the average rate, I didn't want to do the average. I didn't want to talk about that quite yet. So the rate of this experiment, the rate of this reaction, the rate equals change in product. Right, my change in product is I started with 0 carbon dioxide and I made 26. So my change in product was 26 centimeters cubed, 26 centimeters cubed of carbon dioxide. And that happened over 5 minutes. So my rate is going to be 26 divided by 5. Not overly complicated. Forgot my calculator at school as well. I've forgotten so many things at school, it's terrible. So 26 divided by 5, and I get a rate of 5.2 centimeters cubed per minute. So the great thing is the rate equation gives you its units too. Yeah, because you literally are doing what we were doing before. So we've got centimeters per, that means divided by, and it gives you the unit from the rate equation. It's quite nice that you can get lots of different units for rates. So we can work out rates just by simply looking at the change in amount, change in the concentration of product or reactant over change in time. So we pick up the rate equation. So I can tick that learning objective off. Okay, now we need to talk about how can we speed up reactions and particle theory. So actually, what I'm actually going to do is I'm going to reverse these two learning objectives. I'm going to do particle theory first. Okay, can you put a subtitle, please, of particle theory? Particle theory. Okay. Yeah, so this is particle theory. So in order to teach this, I'm going to use an animation for most of it. So particle theory was, first of all, invented by a gentleman called Thomas Dalton in the early 1800s. He invented particle theory as a method of being able to run calculations, to improve steam engines. He treated steam as particles, which no one had ever done before. And it created the very first atomic model, which was called the Thomas Dalton sphere model. So what we can see is that particle model, what we can see is that particles are always moving. Yeah. Now, we always tend to find that there are always some particles moving really quickly, and you can see which one I'm talking about, the one that's going around the quickest, but there's always one that's moving really slowly as well. And then everyone else is kind of in between. So we know, number one, particle theory, number one, particles have kinetic energy, and are moving randomly. They're moving randomly. Okay. So particles have kinetic energy and they are moving randomly. The next thing is, what happens in terms of that energy when particles collide? When particles collide, what do you notice happens in terms of the particle's energy? So what's happening here is that during a collision, energy can be transferred. In fact, energy is transferred. So number two, during particle collisions, energy is transferred. Okay. So now we have like a basic understanding of what the particles are doing in terms of their behavior. We can now look at this now from a chemistry perspective. So in chemistry, what we now need to have happen is you need to have you need to have a reactant. So I can add now another reactant. So now I have reds and blues. Now those reds and blues, when I press go, they're going to be moving around the screen. They've got kinetic energy, and they're going to move randomly. And we know that they're going to collide. Now, when they collide, one of two things can happen. And I'll show you this now. So, okay, so the A's and B's, when they collide, watch what happens when the A and B's collide. And the simple thing is, they bounce off each other. So reactions. Little subheading of reactions. There was a reaction. Particle A and particle B. For a chemical reaction, to occur, particles must collide. Because you can't just have, if you just have one type of particle, reset, and I take that out, there can never be a reaction between these because they're the same particle. Yeah? So those can bounce around all day long. You could potentially get a thermal decomposition reaction if these slammed into each other hard enough. It could cause the A to break down. But in this case, that these are singular particles, that we're going to avoid that particular scenario for now. But when there's only one reactant, no reaction. Yeah? So for a chemical reaction, particles must collide. But that's now not enough because like we saw before, if I put the A's and B's together, they are bumping into each other, but there's not always a reaction. In fact, the key to this is must collide. However, there's a big thing. I'm going to put this in red. However, put it in a star. However, most collisions do not end in a reaction. They simply bounce off each other. They simply bounce off each other and move off in a different direction. However, every now and again, restart. Every now and again, there will be a collision. So reds and blues, there was a successful collision. Let's keep an eye on those reds and blues. We need to still see when there's an unsuccessful collision. There you go, and a red and blue collided, but there was no reaction. There was another red and blue collision with no reaction. So most collisions that take place do not actually, there was a successful one. Now I wonder how many of you can figure out as to why is it that some end in a reaction whilst others don't? What's different about the reactions that are being successful? What's the difference between them? You guys can post on the chat. Okay, so however, most collisions do not end in a reaction. They simply bounce off each other. So when do they react? When the particles speed. Hao Ping, what did I say about that word? Can't believe you just wrote that down after I had a big go at not saying it. Hao Ping! But by the way, well done to everyone else. They must have enough energy. Correct. The ones with higher energy. That's correct. So when particles collide with enough energy, and I'm now going to put underneath this, enough energy, there will be a reaction. Right, I now need to highlight this, enough energy. This is given a word, it's given a name. Yeah. Yeah, this is change my color. Let's go for green. activation energy. Now this has a definition. The minimum amount of energy required for a successful collision. Cool. So we realize that EA, yeah, I love the fact that you've given me the symbol helping EA. I'm actually going to make that a better E. EA. There we go. Symbol for activation energy. So it's nice for us to understand, go back to my learning objectives. We now understand particle theory. We can look at this in terms of particles must collide. Particles need to collide with enough energy, and that enough energy, that minimum amount of energy required for a successful collision is called activation energy. Okay. So, what could we do? New subtitle. Factors that change rate. Not that horrible word helping. Grr. Factors that change rate. Okay, so here's my reaction. I want it to go faster. Guys, what can I do, please? I want to increase the rate. Shouldn't say the word faster either. Shouldn't be used. I want to increase the rate of this reaction. What could I do, please? Give me it on the chat. Halping's given me 2 brilliant ones straight off the bat. Like it. 1, 2, 3, 4, 5. So Halping has given me. Oh, there's Tiffany. There's Lara. Heat up. Yeah, heat up. Lara and Tiff have given me the right answer. Use a catalyst. Well done, Alison. Number 1, we know factors that change rate. Temperature. Yes, temperature. Factor number 2, concentration. Concentration. That's French for concentration, by the way, if you're not sure. The next one is pressure. Yeah, pressure. We've also had decreased volume. No, volume's not one of them, but you've said something that's close to the right answer, but it's definitely not volume. Volume makes no difference. Number 5, thank you so much, Alison. Use a catalyst. No one has given me number 4 yet. Lara's on the right kind of lines, but she's definitely given me the wrong answer. Anyone else? Come on, guys. One more. I don't want to give it you. You guys have done so well. You guys know this. I've been teaching you guys long enough. Think biology. Oh, think biology. Come on, everybody. Come on, everybody. Yes, Audrey's on it. Surface area. Thank you very much. Right. Now, one of the things that I love about rates is that it's just common sense. Yeah, well done. Caitlin, concentration's already been said. But yes, Audra, well done. Alison, Sophia, essay, yeah. Right, so temperature. Let's increase all of these. Increase temp. What happens to, if I increase temperature? Okay, hang on a minute. Yeah, let's go. Change. Rate change. Change. And change in rate. See what I've done there? Love it. So we're going to increase temp. On the chat, please. What's going to happen? I think the chat is very laggy. It is very laggy. What's going to happen to the rate if I increase temperature? I'm going to increase concentration. What's going to happen to the rate? I'm going to increase pressure. What's going to happen to the rate? I'm going to increase surface area. What's going to happen to the rate? I'm going to add a catalyst. What's going to happen to my rate? Helping, well done. First one, increase. Well done. Just going to do this with a red pen. Increase. Well done. All increase is the right answer. Increase, 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 increase. I love rates. I love kinetics. Yeah. The best thing about this is the fact that we realize that all of these increase the rate. Amani, try not to say faster. Yeah, it shouldn't say, oh, I can't even say it. I'm moving on. So they increase the rate. Guess what happens if I decrease all of them? They all decrease. It's amazing. I love rates. It's so easy. It's so common sense. It's really, really nice. So hang on a sec. Hang on a tick. I've actually come to my end of my lesson now, almost. Factors affecting rates. But I just want to apply something. Guys, look at our thought experiment. So in the first minute, we made 10 centimeters cubed of gas. In the second minute, I made 8. So we had 10, then we had 8. And then in the third minute, I made 5. It's just the difference between them, by the way. Gone up by 8, gone up by 5. The next one only goes up by 2. The next one only goes up by 1. And the last one's 0. Guys, here's my question to you. Why is the reaction slowing down? Let's watch one of these. Let's watch one of these. No, already rates. Is the right answer helping? Well done. So when the reaction starts, the reaction happens really quite quickly. So after 7 seconds, after 9 seconds, nearly all of it's used up. And then this last one, there we go. So it took 9 seconds to clear 3 and then took 6 seconds to do the last one. Yeah, all energy is transferred. No, Caitlin, energy is always being bounced around all over the place all the time. It's finished. No, but hang on, it hadn't finished. It was slowing down. Why is it slowing down? Haoping's got the right answer. So this is the last thing I want to leave you with today. So reactions, as reactions proceed, as reactions proceed, as they happen, as they proceed, they slow down. They slow down. The start of reaction, no, not the start, wrong word. The beginning, the early stage of reaction is high rate. Reactants get used up. Reactants get used up. So their concentration decreases. The rate slows down. Rate slows down until it finally stops. Reaction stops when all reactants are used up. Does that make sense? Why does the reaction ever stop? Because I ran out of reds. Yeah, if I restart that, look how long it takes for 2 to disappear. Yeah, so we're just going to keep an eye on that clock. 1 gone already. 2 gone. 8 seconds, 2 are gone. Last 2 still there. Right, 3 were gone at 11 seconds. 3 were gone at 11 seconds. We're now at 20 seconds, still 1 to go. And the reason being is the concentration of the reds has dropped significantly, and that of the blues. And they're less likely to collide with each other. Yeah? Their collision frequency will decrease. Fewer particles per unit space. And there's the final one, 35 seconds. Now we can increase that. If I increase the temperature, I'm going to give the particles more kinetic energy and make them move around quicker. What that means is they're much more likely to collide with each other. That one took 35 seconds at that temperature. Still slowed down towards the end, and they still haven't collided. At 35 seconds is what we're trying to beat, and there you go, 12 seconds. So it's nice for us, Speedy Gonzalez. No more successful collisions. So we can actually draw a rather beautiful graph. This is your very first time seeing what's called a rate graph. So what we're going to look at in this graph, this is time. Let's put it in seconds, why not? And this will be product. Now we can do grams of product or CO2 if we like. And what happens is, so this is where I want to see if I can do something. Check this out. Okay, I'm going to try doing something now, guys. I'm going to turn this down. Okay, I'm going to try and plot this rate graph. So I'm trying to do it via seconds. So go, and then I need to pause it when a reaction stops. Whoa. At 1.65 seconds, 2 products have just been made. So at 1.65 seconds. So I'm going to start at 0, going to go to an unknown number. Let's go to 35 seconds, because that was what it was about last time. At 1.65, we've got the total number of yellows that we can make is 4, yellows and greens. Let's just count the yellows. So at 1.65 seconds, let's make this an easy number for us. Let's make this 40 seconds. That'll be 20 seconds. This is 10 seconds. That's 5 seconds. That's 2.5. So about there. So we've just gone from 4, and then so it's 2, so that's 3, and that's 1. We've just gone from 0 to 2 in 1 second. Right, now we're going to look at the time taken to make the third. Well, that's interesting, isn't it? Stop. 14.93. Right, 14.93. Well, there's 15. To make the third goes to here. Right, what about the fourth one? Oh, an unsuccessful collision. That was frustrating, wasn't it, folks? Very frustrating. We need those red and blues to pick up some energy from a collision. There's a fast blue. Come on. Oh, there we go. Stop. 35. Perfect. So that's 30, and there's 35. So the last one to get to my 4 was 35, which is there. And look at my graph. Yeah, there's my graph. So what we realize is, and at that point, it's now going to be even, that's now, of course, going to become level. So we get this rather nice, lovely graph of like this. Yeah, that's the graph we're getting. So at the beginning stage, this stage here is really, really high rate. Yeah, this is going at the highest rate because it's had the highest concentration. It now starts to slow down. Yeah, it slows down because it's being used up, concentration drops, and then it finally ends at the end when all the reactants are finally used up and the graph levels out. So it's nice just to look at this and see what's happening in terms of the particles. I'm going to end the lesson now at that stage. Going to end it there. I'm going to then go back to this. Hey guys, right, I'm going to try and I'm going to end this and drop back onto the Google Hangout. I'll see you shortly, guys.